up and running, full screen. Very bright day here. A lot of sun streaming in. Hopefully the board will be visible at all times, but if it doesn't come out, I guess I'll have to do it again. All right, so rule in my class, it's an Algebra 1 class, and we're ready for, I think, a simpler and easier way to put a typical Algebra 1 problem, putting quadratics in graphing form. Quadratics, fancy term for rectangles. Quad, four-sided Latin, right? And so here's a very typical problem. User-friendly numbers so that we can see concept, not get bogged down in computational difficulty. The goal is really to be able to graph that and find the roots in 30 seconds or less. It's doable. So that's a goal. And these are typical problems. So I teach from a holistic perspective, which means that I throw a lot of questions early on to students, and God, I hope this comes out. I know I'll get a lot of different shadows and everything else. And so whatever I ask on day one, I ask on every test for the entire semester. And questions right now, we've got about 100 questions on a final exam coming up in 2 weeks. And I'm looking for students' best score. So people learn at different rates. And as long as you can convince me that you've gotten a particular question topic down, I'm going to give you credit for it. So I'm going to summarize our trip through quadratics this semester and end up with, which actually is the easiest way to graph a quadratic. Then as the video progresses, I'll explain conceptually why we can do it. And I don't think it's built on anything other than Algebra 1 concepts. And yet it's going to be an early foray into calculus. All right, so let's have at it. So early on in the semester, we looked at the trajectory of squaring. We looked and tied it to geometry, squares. I think I'm showing you squares. -3 times -3, 9, to 4 to 1 to 0, to 1 to 4 to 9, very friendly numbers. And we talked about decreasing areas, decreasing, reading graphs from left to right, decreasing, and then increasing. And there seems to be a most important, right? -1 still got us 1, shared y values, but there's a most important place in that process. And it appears to be here. Appears to be there. And we also talked about average rates of change, from one location to the next. How do we measure change? Change in y, 9, 1, change in x, from -1 to 3 is a change of 4. And so this secant line is what it's called, is going up at a 2-to-1 ratio from this xy value to this xy value. And of course, that's our famous formula for slope, y2 minus y1 over x2 minus x1. So we're doing some pretty standard stuff. But then the question is, what happens when we try to graph 2x squared minus 20x plus 7, when we bring in more terms? Well, one thing we have to look at is the difference between multiplication and squaring. If I take a number like 100 and square it, I get 4 zeros. Where if I multiply 100 by 5, I get, 500. And this dwarfs that. So this is the dominant term that's going to affect trajectory. So we're still going to get a cup shape up. We had conversations about that. And we said, well, how do we solve most equations? I'm sure we were already writing equations of lines at that point, solving linear equations and dealing with inverse operations. Well, the problem with this is I can't take a square root because this isn't a square. If I look at all ax squared plus bx plus c problems, I can see a rectangle out of the first 2 terms. And hopefully you can too. And if you don't see it on day 1, remember, we repeat these conversations for a minute or 2 every day. So my suggestion is, look at the video a couple of times. If you look at it 4 times, this is going to be a half an hour because we're really going to get into a deeper dive here. But if you really want to understand what's going on, just watch it 4 days in a row and you'll own it. It's just how the brain works in terms of processing math, I think, for the average person. 4 days, ownership. So I factored out an x for this. And then I wrote x times x minus 10, which is x squared minus 10x, right? And if I double that, 2 times x squared does get me the first term. 2 times minus 10x does get me minus 20x. And then if I add 7, then this is a geometric representation of that. I can't use inverse operations. I can't use a square root because that rectangle is not a square. So somebody way back when, 1,000 years ago, maybe, I don't know who completed the square first, said, well, let's reconfigure it. And I think I actually did this over here. I tried to keep this in some kind of order, but I think it's important. Oh God, I hope this comes out. So if I'm looking at this rectangle, 2 times 10, I get 20 units of area. But I could reshape that by making the longer side shorter and the shorter side longer, and a 6 by 6 is 36. And 36 minus 16 is 20. So those calculations give me the same area. So in general, all ax squared plus bx plus c can be expressed as ax squared plus bx, if you use these as the dimensions, plus c. There's our rectangle, which means that we can do what? We can make a square out of it. All right, so if I wanted to make a square out of that, I know I've got to cup shape up because of the dominant term. All right, well, what gets rid of the area? I think we can see if the x was 0, 0 times anything, no area. That's going to get us c. Right? And also, what makes ax plus b equals 0? Well, minus b over a. Right? 2 inverse operations. And maybe I should plug it in here so you can see how it works. A minus b over a. A's cancel, b's cancel, and I get 0. So I'm not telling you what b is, a positive or a negative number. It's just 2 roots, getting me a constant. Well, what's the important place on a quadratic? Important place on a quadratic is right there. Right? And of course, we practiced how to write quadratics given random numbers. We've been practicing this. Let's say 5, 7 goes through 11, 20. Right? That's a 3-second calculation. Okay, so if you know, let's see, do I have an eraser here? Yeah, so if you know, and we started talking about the graphing form for a quadratic, HK, where HK is the vertex. And so all of these are early conversations, probably in our first work of the semester. All right, so how do we find H? Well, what's between 0 and minus b over a? All right, what's between 2 and 10? Well, if you add 2 and 10 up and divide by 2, well, that's where you're getting the 6. So if we add these things up, 0 and minus b over a, I'll put it in parentheses and divide by 2. Well, we're halfway. Minus b over 2a is halfway from 0 to this. And that's right darn smack in the middle. So we can easily find our x value of the vertex by minus b over 2a. Of course, more conversations have to be had with respect to the geometry of the problem. Now, where was the geometry? Geometry of squaring's over here. Well, again, I hope this comes out. This is unique. 0 squared gets me no area. And if you square a positive or a negative number, you're not getting 0. Right? If I square any positive and negative number, I get the same answer. I get a repeat of an answer. But there's one place where I only get 0 once. Right there. All right. So therefore, we want to make our x value act like a 0. Right? And so if I found, I guess I'm ready to put this in graphing form. And this is the way we did it originally. It's not the fastest way, but it's certainly a lot quicker than drawing the rectangles and completing the square. So I am going to look at minus b over 2a. And if I do, I have the opposite of minus 20 is 20, and 2 times a, which is 2, gets me 5. So that means that in the graphing form, I can now replace h with the number 5, because 5 minus 5 gets me 0. But I don't want 0. Where did I do this? I'm trying to do 5, 7 to 11, 20 in 3 seconds or less, but I'm talking about it because I'm probably not familiar with this process. But a 5 now gets me 0. I want 7. I write 7. And then it's just a question of finding the multiplier. And I got the marker, I can make this work. I can tell you what 11 minus 5 squared is. It's 36. 11 minus 5, that's the second x value. 11 minus 5 squared, one more operation than the linear, gets me 36 units of change. Do I want to go up 36 from 7? I don't think so. I want to go from 7 to 20. I don't want 36 units of change. I want to go from 7 to 20, 13. So we were practicing this as well. Okay, and of course, once we've got this, we could set it to 0. Not that this is user-friendly, but we could do inverse operations and we could find the roots that way. And so we started doing that a little bit, and it takes time to learn it. And, you know, a lot of tests, a lot of chances to learn it. Just show me before the end of the semester you can do it. And most students now can do that pretty easily, solve that. So where am I now? So I'm over here. I guess we had the discussion. 0 minus b over a, so minus b over 2a. Repetition's our friend, right? And so the function evaluated at minus b over 2a is going to get us the y value. So back to this problem. So minus b over 2a, 20 divided by 4 is 5. So we now know 5. And if I plug 5 in, I get 50 minus 100 plus 7. And if you're looking for patterns in math, that looks interesting to me. So that looks pretty interesting to me. So let's look at binomial squaring. Let's look at x minus 5 squared. And I think some students have had some familiarity. Let's call that x, and let's call that x, and let's do minus 5. And let's do, it's got to be a little lower here so that this looks like boom, boom, right? Like terms here, right? So you have x squared, you have minus 5x, you have minus 5x, and you got 25, but I'm just going to write a constant here because I want to look at the quadratic and linear terms, especially if I put a 5 in. So let's put a 5 in here. What happens when that's a 5? Well, 5 times 5 is 25. 5 times negative 5 is minus 25. And again, minus 5 times 5 is minus 25. And I see a 2 to 1. I see minus 50 for the linear component and 25 for the squaring component. And I see that 2 to 1 opposite relationship. And that only happens at the vertex. All right, so it's a nice check on whether you make a sign error or not in one of your calculations. So we practice that. So once we had 5, the shortcut then is, well, 50 minus 100 plus 7 is minus 50 plus 7. And we notice that when we plug it in here and we add these two, you get half of that. And if I add that, I get minus 43. And so that's our vertex. And so we now know we have a cup shape. 5 gets you negative 43. And we also know the y-intercept from the scratch, 0 gets you 7. And so that allows students to see negative 43 to 7 is 50 units of change. And from 5 to 0 is backwards 5, but we're squaring. 5 units of change gets me 25 units of area. And 50 divided by 25 is 2. And we said, wow, what a nice coincidence. Yes, it's not a coincidence. The A term of a quadratic is rise over run squared as measured from the vertex. And I don't think that's relatively speaking, known by too many people. Don't know why, and why that isn't just common knowledge, but it doesn't appear to be. All right, so that is the conversion for a quadratic from the vertex, rise over run squared, measures is the adjuster. I'm not going to call it slope because it's not slope, but it's the adjustment necessary so that the values go through what they need to go through. And so now let's put this in graphing form quickly. Let's not put it in graphing form. Let's just graph it. All right. The way that we learned in class was, well, a negative. Cup shape down. Minus b over 2a gets me a 2. That means my 0 is on this side. Right. And that gets me minus 7. And I'm one step away. Putting in a 2 gets me 24, cuts in half. 12 minus 7 gets me 5. And I'm done. All right, so then we said, okay, let's put it in graphic form. A 2 gets you a 5, so x minus 2 squared plus 5. And we already have the A term. We don't have to find it. We could, How do I get from 5 to -7? I go down 12. What's the square change from 2 to 0? From 2 to 0, square change is 4, and 4 goes into -12. Oh, another coincidence. All right, but now we can find the roots pretty easily. Because I don't think I would have started. Yeah, I'd start with this one. The roots are real, no imaginary roots. So what do? We subtract 5. We divide by -3. We do the inverse of squaring, plus minus square rooting. I may be losing this on the camera. Not yet. Oh, finish it off. And then -2 goes to the other side, becomes +2, plus or minus 5/3. Those are the roots. And we check the roots by plugging them in and just seeing the inverse operations at work, which is 2 plus minus the square root of 5/3. All right, so what happens to the 2's? They cancel. All right, so I'll just get them out of the picture here. Squaring a plus minus gets me a positive. Squaring a square root gets me what's inside. I've now done that operation. Oops, I wrote the wrong thing here. Didn't see that. So I'll correct it, but I won't be doing the video again. I don't know why I wrote that there. And so good thing I'm checking. So -3 divided by 3 becomes -5, plus 5 is 0. And we can see that that works. All right, and so then we just looked at our answer, and that's a good habit to get into. Always look at your answer. What are the roots? The roots are 2 plus or minus the square root of 5/3. And we said, well, wait a minute, I see that there. Boy, I probably could put that there immediately every single time. And we're looking for roots. Well, how do you get from 5 to 0? You got to have 5 units of change. Yeah, and of course, if you're multiplying by 3, division, we said, wow, we don't even have to do the equation out anymore. The answers are right there. Now, it took a lot of students, some students a day or two to get that, and others a week or two. And some are still working on it. All right, but for the most part, people write their answer in 10 seconds or less and move on. All right, so I already talked about average rate of change. And so now we're still trying to get the quickest and easiest way to write quadratics in graphing form, fancy term for rectangles, turned into squares, into graphing form. And so we're going to take a deeper dive into not average rate of change, but what if we take a microscope and just talk about changing from one location to another that's really close? That should give us a sense of the rate at which the function's changing near that value. So we put some numbers in, at least I did. And of course, I've seen the pattern, so I don't need a calculator. I know if I started with 2 decimal places and squared it, I get 4 with a 1 at the end. And then I did 1.001. I did 3 decimal places, and I squared it. I ended up getting 1.003001. Then I squared 2.0001, 4 decimal places, and I got 4.00. I did this one wrong. So I did 2, so that should be a 4. Corrected it on the run here. Okay, and so I should get 4.4 decimal places with a 4.0001. And if I did 3 with 5 decimal places, I'd get 9 point. Maybe you can pause the video now and tell me what I'm going to get. That's when you really learn mathematics, is when you start looking for patterns yourself. All right, so pause the video. I'll just write it. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Well, there it is. And we say, okay, well, let's look at the instant 0. I'm going to divide each of these by 2 decimal places and get rid of the stem. 3 decimal places and get rid of the stem, so on and so forth. Well, 0.01 goes into 0 times. How many times does, where did I get that from? 3. Boy, I'm making big mistakes here. That's because I did a cubic video last week. I think it's still in my head. That should have been 1.002, but I'm not doing this again. Then this one is 0.004, so that divided by 0.0001 gets me 4. So this gets me 2, 2 gets me 4, 3 gets me 6. I wonder what 4 is going to get me. Yeah, you're right, 8. I said, well, wait a minute, there's a nice pattern here. Sure looks like we're doubling the x's to get the rate of change at that instant. And so let's just do a little slope field. So at 0, I'm flat. At 1, I'm going up at 2 to 1. At 2, I'm going up at 4 to 1. At 3, I'm going up at 6 to 1. And I start seeing the outline of the right side of the quadratic. Yeah, using the slopes. I still think that's not that difficult to understand. I don't think you have to wait to get to a calculus class to have this conversation. I should have had the camera up a little further. So it's going to be a butchered video here, but that's okay. And so now I want to look at this from a geometric perspective, which means I got to go get another board in here because I don't have enough room for this. Back. So let's look at this a little bit geometric. I'm doing a video now. You'll have to come back. Yep, student who wanted to work at 9 o'clock, but it's 9:30 and I wasn't waiting around the whole day. Yeah, so here's the geometry of the situation. All right, and we've got our squaring process. And I decided to look at a 3 by 3. And we said, remember what we just did? Can you see that? Let's come back a little bit. So if I put a 3 in, and I put I guess 0.001, 3.001, 3 squared is 9. This should get me 9.006001. Okay, that's what that should get me. And so we basically are looking at that change. Why? Because it's a layering process. Here's a 3 by 3, 9 units. If I increase by 0.001, well, I can't show it. It's too small to show, so I'm blowing it up, but I get new area here, and I get new area here. What's the new area here? 0.003. What's the new area here? 0.003. If I add those two up, I'm getting the 0.006. Where there's a little error is on the cusp, but if you multiply 0.001 times itself, if you square it, you get 0.000001, and that's the kind of the ending, the ending aspect of this calculation. And we can push that error out so far that it's negligible. And when I mean negligible, it vanishes. All right, so that's kind of the geometry behind the change. And it sure looks like if y equals x squared, then the change in y over the change in x, and we use different symbols when we zoom in, difference in x. Well, what's the difference in the x's from 3 to 3.001? Right, 0.001, but it could have been a smaller difference. Smaller, 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 smaller. So we're just going to say dx. And remember that we're putting numbers that are very close together with how many decimals? More than you can imagine. But we're getting the same answer each time we do it. Right now, our difference in y's can be big, small, positive, negative, 0. But it sure looks like that's 2x. So we're getting to our goal now. Our goal is to be able to do graphing a quadratic and getting the roots as quickly and easily as possible. We're almost there. We're getting there. All right, so here's a particular, just another example of a basic Algebra 1 type problem. And I don't know why I'm writing that, but yeah, because I changed it. I think I didn't want the same numbers to show up. So what is the change in x squared? The change in x squared is based on the two sides of the square, 2x's. Right? I mean, I could have, instead of a 3 by 3, here's a 3 by 3. Right? I could have done a 2 by 2, could have done a 2 by 2, and that's going to change at a different layering process than the 3 by 3. The bigger the square, the longer the length of the rectangles. And yet I'm standardizing my 0.001 by calling it dx. All right, I could have done a 1 by 1. I could have done a half by a half. I could have done 0 times 0. It's a square, I can't draw it. And so what's going to have the rate of change with no magnitude? Well, obviously the 0 times 0 is where something's going to be flat, no change. Remember what we said here, 0 squared is 0, but 0.001 becomes 0.000001. Not changing. Whereas at 3 got us 9, but 3.001 got us 9.06001. Significant change. So the rate of change, oh, I know what I had here. I had 3x squared. I changed that number on the fly so that you could see that that's made up of one graph, 3x squared, plus second graph. I guess I changed this and forgot to write that. So I changed this on the fly. So minus 30x is a linear function. 3x squared bottoms out at 0. And so if you add these two graphs together, you're really adding the rates of change together too. And so this graph is coming down, this one is going up on the right. At some point, their instantaneous rates of change are going to offset each other and we're going to bottom out. So the quickest way is to actually use the rates of change to graph. So let's cut to the chase and let's get over here and do it. All right, so 2x squared minus 20x, I know x squared, the rate of change is 2x. And if I double something, well, that's going to be part of the associated rate. I'll give you an example of that. You make $25 an hour, and I triple your rate. Dollars per hour, right? $25 an hour, but if I triple your rate, boy, you just did a quick calculation and you understand something about multipliers and rates. All right, so this rate is 2x times 2, and linear functions, they change at a constant rate. And I think that's a discussion we want to have, even though we're really beginning to work with our first derivative. Right? That's an algebra 1 concept. I go down 20 over 1, down 20 over 1, down 20 over 1. If I did that consistently, sure would have looked better. Down 20 over 1, down 20 over 1, down 20 over 1, and we see our data line up. All right, so what's the rate of change of that? Minus 20. And what's the rate of change of 7? You keep looking at 7. Tell me when you see it change. I think in other videos, I've always said the same thing. If you see that number change, please get in touch with me. All right, we'll get you some help in a nice way. Okay? Constants don't change. So therefore, we have 4x minus 20 bottoming out when the slopes are 0. And we can see that that happens at 5. Now, what's minus b over 2a? Minus b, 20 divided by double the 2, 4. Oh, same answer. Nice coincidence. Nice coincidence. But it's actually easier to look at this and simply say, double it. Leave this alone and set it to 0, and you got yourself the x value of the vertex of a quadratic. All right. So I'm going to do that with 2x squared minus 20x. I think it was positive 2. 2x squared minus 20x plus 7. So how would I graph this? How would I find the roots in 30 seconds or less? By doing the following. Well, I got one more thing to show. I want to prove that the rate of change at 0 is minus 20. So let's look at change. 2x squared minus 20x plus 7. And let's do 3 decimal places for x. Let's start with 0. 0 minus 0 plus 7. And then let's go 3 decimal places, 0.001. And I'm going to I'm going to square it and double it. So I got 3 decimals. That becomes 6. 1, 2, 3, 4, 5, 6 decimal with a 2. This one here, I'm going to multiply that by minus 20, which gets me minus 0.020. And this is no change. So if there's no change there, insignificant change there, it looks like I'm changing by this amount. And if I divide that by 0.001, I get minus 20. So at 0, this function is going down at that rate. All right, now I'm ready to do the 30 seconds. And maybe I won't talk at all. Maybe I'll just do the graph based on that process. Remember, this is going to become 4x minus 20. And I'm setting that to 0. Okay, I think I can do that in my head. All right, so what am I going to do? I see cup shape up. I now know that I'm on the decreasing side. 0 gets me 7. And now 4x minus 20 tells me 5 is the important number. Minus 100 cut in half is minus 50 plus 7 is minus 43. That's the graphing form now. I could put in graphing form, but I want to know when I hit a height of 0. So therefore, I know I'm measuring from 5. Plus or minus, I know I'm going to take a square root. How do I get from minus 43 to 0? I go up 43 units. I didn't write that well. And my A term is a 2. Okay, so that should be the roots. Let's check it by putting it in graphing form. Got to get rid of that. 5 negative 43, x minus 5 squared, making a 0 out of the number 5. Minus 43, taking 2, solving this. Oh, I was going to just plug the answers in. Well, let's solve it. You can see where all the things I did came from. So if I set that to 0, what am I going to do? Minus 43 is going to the other side, becoming positive 43. Boom. Positive 2, multiplication on this side becomes division on this side. Boom. Squaring becomes plus minus square rooting. Boom. And minus 5 becomes positive 5. All right, so let me put that back in the graphing form with a space for the answer. And let's see if we do get to 0 when we put our answers in there. 5 plus minus the square root of 43 over 2. All right, so what happens to the 5s? They cancel. What happens when I square plus minus? Just get positive. Squaring a square root gets me what's inside. The 2's cancel, and 43 minus 43 is 0. That's the quickest way to do this. I'm not going to hold anybody on my class responsible for doing that, but I want to plant a seed to connect the layering process of the squaring process to two sides of the square. If you're doing a circle, there's the area to the circle. What is gonna, area is pi r squared. That's also a parabola. So if I have a radius going out and the radius, if I just snip it and call that change point 001, then the layering is the circumference. All right, circumference is what dictates the rate of change for area of a circle. If I had a cubic, and this was a video I did a week ago or so, right? It's always one dimension below. Cubic is a three-dimensional shape, but at what rate does it change? That sleeve, right? That sleeve is surface area. So the volume is connected to the surface area. That makes sense. They got to be connected. And this is the stuff you'll study at future courses, but I think it's important to get some of those concepts in front of us to start discussions. Longer time you talk about something, the deeper your understanding gets. So now we'll just do two problems, almost done. I do want to talk about an imaginary solution. I hope I did create one there. We'll find out. If not, I'll change the constant. But now we're doing 3x squared minus 12x minus 5. Let's see if you can do it in 30 seconds or less. I think it takes some practice, 4 days in a row, 2 minutes a day should do it. 3, cup-shaped bubble. Decreasing side, y-intercept, 0, negative 5. Remember, we read from left to right, decreasing side. I am going to look at 6x minus 12, which gets me a 0 at 2. If I plug a 2 in, 2 times minus 12 is minus 24, cut in half is minus 12, minus 5, minus 17. So therefore my x's are measured from 2, plus or minus to get to 0. I have real roots, so it's 17 divided by, what, 3. There's your roots, there's your graph. If you want to put it in graphing form, then all we had to do was take the 3, make a 0 out of the number 2 for geometric reasons, and then we had what, minus 17. And I hope you can set that to 0 and think you got yourself all kinds of solutions pretty quickly and easily. Bring the 17 over, divide it by 3. I guess I'll put the equal sign here. Undo squaring, minus 2 becomes positive 2. And that's what you can see. All right, so let's try the next one. Almost done. And now I'm fulfilling my pledge to always stick with the easiest, quickest way to do something. So let's see if you can follow this. I'm on the increasing side. 0 gets me negative 81. I got 4x plus 24 equals 0. So, oh no, I got 8x, excuse me. Minus 8x plus 24 is 3. And if I drop a 3 in, I'll cut that in half first. So that's 36 minus 81. 36 minus 81, the opposite of that. So that's 51, 45. So positive 45. Minus 45, sorry, because I forgot to change it in that direction. Minus 45. All right. And so now my roots are up here. So my roots are imaginary. All right. So I'm going to measure from 3 plus minus square root. How do I get from minus 45 to, where was I, to 0? Oh, just going up 45 units. And I'm dividing by negative 4. And so I'll put that there, and now I've got myself some answers. Now, it's interesting. I know that we're taught I as a third axis coming out from the wall, so to speak, but honestly, it has significance from a numerical standpoint. So if I wanted to hit 0, I'm going up 45 units. I forgot where I was at, minus 45, right? What I'm really doing is doing a sign change for the A value. Instead of cup shape down, I'm making it cup shape up. And so that's going to be the same answer as if I went down 45 units to 90, negative 90. Right? So let's look at that one. So the vertex was, what was it? I forget. Oh God, it was 3, negative 45, I think. And I think the A term was, geez, I forgot. No, I forgot, darn it. Well, I can certainly make this up. So x minus, no, I can't. Can I? Yeah, I can. So we got x minus 3 squared minus 45, sure. So how do I get from negative 45 to 90? I go down 45. How do I square change from 3 to 0? No, negative 90 is, oh, I got lost. And I don't want to make the video again. It's getting very hot in this room. So, but those x values would match up, except a sign change. All right, so I wanted to do that for my class because that is the quickest and easiest way. I don't have as much practice with that method as I do plugging in minus b over 2a. So a little rough around the edges, but I plan on, when I'm doing my own work, doing it that way, because I do a lot of these. And I want to find the quickest and easiest way, save myself work. It takes effort. And every test that I write, I credit Baba G with effortless effort takes effort. I heard that in a talk one time, and boy, is it true. And if you put the effort in, then you can do something effortlessly. And in the long run, you'll understand it better, and nothing wrong with that. All right, I'm sure I have other things to say because these conversations are endless, but that is a kind of a summary of some of the work we've done this semester. And hopefully it will serve the students well to consider these concepts. I saw an MIT grad talking to a 5th grade class about some early calculus concepts, and I really like seeing it because I think the earlier we start these conversations, the better chance students have to continue their studies and not have to drop out. Okay, so I will post this and hope it helps somebody.